Alright, hello grade 12s. I hope you are well. This morning I'm just gonna cover a bit of a section here on calculus and using the differentiation rules to be able to get, in order to be able to derive, because what's important here is that we are able to derive. Okay, and that's what's key, very, very key. So I'm going to cover a bit of derivation using derivatives and so forth. This is a important section in calculus, right? Because in a typical exam paper, you are usually asked when you are doing calculus the first thing that you are usually asked is to find the derivative from first principles, and then shortly thereafter you are usually asked the question to actually derive using the differentiation rules. So here, what we're going to do is we're going to cover that section, and we are going to find the derivative for these particular expressions or functions. Find the derivative. Okay, so like I said, this is a very important section in calculus in and of itself. So just a few things to note, right? And that is for the notation that is usually used whenever you are deriving. So here we have dx into f of x. Here we have d over dx into f of x, all right? And basically this here means d means the derivative, right? The derivative and the things we need to derive with respect to this variable, which is x. Okay, here we have d over dx, which again means we need to find the derivative, but with respect to which variable? With respect to x. So for this particular function. So here's something to note, that whenever you have the derivative notation here like this, and it's attached to a specific expression or function, what you need to realize is that this here will always disappear the minute you are ready to apply the power rule, or the minute you are ready to derive. This notation will disappear, and then you will derive that particular expression. On this side, you have dy over dx, you have y prime, you have f prime x. Now these three notations, whenever you are ready to derive, they will appear when you derive. So there's a distinction between the utilization of this notation and the utilization of this notation. So the important things that you need to note is that for this notation will always be attached to a certain expression, and this notation will disappear the minute you derive. But these ones, dy over dx, y prime, and f prime x, the minute you are ready to derive that particular function, these three will appear when you derive. So these will disappear, these one will appear. And I'll look at a few examples so that you can kind of internalize what I mean by these will disappear, these will appear. So when I actually do those particular examples, then I will refer to what I meant here. Now, something to note is that before you derive, there's a lot of grade 10 work that needs to be done. So before you even find the derivative, before you apply that power rule, there's a lot of grade 10, grade 8, grade 9 foundational work that you need to first do. So for one, you need to take that particular expression that you have before you even derive, you need to simplify it. Okay, how? Right? There's certain methods of simplification that you learned in earlier grades, right? And amongst the most important one is being able to take note of BODMAS, or BADMAS as they call it. That means you need to take note of your expression, look at the brackets, okay? Look at the exponent. If there are brackets and exponents in that order, you follow through. You look inside the brackets, you check if there's anything that can be done there, like terms and so forth. Then you follow up with the exponents. You check the exponents if there's any application of exponents that you need to do. And oftentimes, any application of exponents means that you need to actually, maybe, if there are brackets and there's exponents, you need to expand, right? Division, please guys, right? When there is a fraction of two expressions, then there are certain rules that we need to apply when we are dealing with the expressions of fractions. Sometimes we need to factorize the numerator, factorize the denominator, and then simplification happens. Or sometimes we need to separate. If there are many terms in the numerator and a single term in the denominator, then we need to separate the fraction so that simplification can happen. All right. Yeah, and there are exponential laws that can be applied with exponents. Multiplication, definitely multiplication. If there is any multiplication in that order, addition, if there's any addition, and subtraction, if there's any subtraction. Okay, and like I said, there are certain aspects there in your simplification where factorization may be needful. Then the whole objective of basically simplifying before you derive is so that at the end you want to have separate terms in your expression, distinct separate terms. Why? So that you can go ahead and apply the power rule for derivation. But even before that, you need to make sure that in your expression before you derive, all variables are in the numerator which you are going to be deriving with respect to. So if you are going to be deriving with respect to x, the variables x need to be in the numerator. Also, all your variables, if there are roots, before you derive, your roots need to be changed to exponential, form. So you do all of this change of roots to exponential form, you do it before you derive. Okay. I'm going to look at a few examples so that you guys can actually internalize what I've just explained here. So the first question that we have here is we need to find the derivative, okay? And here we are told dx brackets into x minus 3 into x squared plus 1, close brackets with the full on bracket. So let us look at this particular question. So we are asked to derive right dx. So we are expected to find the derivative with respect to x, and as you can see, this dx is then attached to this expression. So as I had said before, what we first have to do whenever we are doing these questions is that we need to look at the expression inside the bracket, and then we want to first simplify it. Whilst we are busy simplifying this expression, dx goes nowhere. Dx stays with the expression until we are done with the simplification. We need to first simplify this expression, applying methods that we have learned in earlier grades, grade 8, grade 9, grade 10, and so forth. So in grade 9, when you have two brackets like this, right, you are going to remember BODMAS or BEDMAS. Brackets, right, two brackets. Okay, inside these brackets, there are two terms. Inside these brackets, there are two terms. There are no like terms inside each bracket. So that means as far as BEDMAS is concerned, brackets, there's nothing we can do inside the brackets. Secondly, exponents. Okay, we can see that x to the power 2 is there. It's plus 1. After that, we think of division, we think of multiplication. Now, brackets mean multiply in mathematics. Brackets mean multiply. And in grade 9, you learned that a binomial times another binomial can be simplified further. We can expand this here. So how do we expand it? All we simply do is we apply a method called FOIL, where we multiply the first terms, we'll multiply the outer terms, we multiply the inner terms, and then we multiply the last term. We apply FOIL. So that's what I mean, guys, that when we are deriving in grade 12, before we even apply the power rule or derivative, we first need to actually expand what we have. As you can see here, this requires us to expand because we have two brackets. They are obviously there with two terms in them. So this is binomial expansion. We expand this particular binomial. So how do we do it? We say x times x because brackets mean multiply. So x times x squared will give us what as we simplify? Okay, so I'm just gonna write this here. X times x squared. Whenever we are multiplying bases that are the same, we keep the base, then we add the exponents. So this is 1 and 2. 1 plus 2 gives us 3 as the exponent. Then we say x times 1. So when we are multiplying out, we are always considering the sign, the number, the letter as we multiply out. We make sure that we multiply the sign, the number, and the letter. So for instance, the x and the x squared, a positive times a positive gives us a positive. There's a 1 here that's invisible. That 1 times 1 gives us 1. Then we'll follow it up. We follow it up with the letter. The x times the x squared gives us x to the power 3. Sure. This is so irritating. Then there's x times 1, right? So positive times a positive gives us a positive. X times 1 gives you x, all right? Then we multiply the inner term. Negative 3 times x squared gives us negative 3x squared. And then last but not least, 3 times 1, all right, gives us negative 3 times 1. Negative times a positive is a negative. 3 times 1 is 3, all right? So now what we've just done is we've just expanded this particular expression. This particular binomial times this binomial. And so then what's left for us to do is that we can actually do what? We can now derive this expression because there are 1, 2, 3, 4 separate terms. Okay, so now we can derive with respect to each individual what? Term. Because here, if you look at here, there's no like terms. Okay, this is x cubed, this is plus x, this is negative 3x squared, and this is negative 3. So this is 1, 2, 3, 4 separate terms. Okay, so now we can go ahead and we can derive with respect to each individual what? Each individual term. So when we derive, you remember what I said here? I said with this notation, dx, d over dx, what we can simply do with this sort of notation, we can go ahead and then make the notation, this one, disappear when we are ready to derive. So now we are ready to derive because this has been simplified sufficiently. So we can derive each respective term. So when you derive each respective term, this is how it happens. So this x to the power 3, we then take the exponent, we multiply it with the current coefficient, which is 1. Then we retain the variable x. We subtract 1 from the exponent that is already there. So this is 3 times 1, x to the power 3 minus 1. So we've just applied the power rule to the first term. And we do that to the next term as well. Apply the power rule to this particular term. This one, there's an x to the power 1. So what happens is that the exponent, we write it here, gets multiplied with the current exponent. We retain the variable x, and then we say 1 minus 1. Okay. Then this one, this term, we do the same thing. All right. This exponent gets multiplied with the current coefficient, which is 3. We retain x, and then we say 2 minus 1. And lastly, the derivative of a constant term. Now we say that the derivative of a constant will give us what? 0. All right. And then now we're ready to basically go ahead and simplify this here. So it's grade 12. Doing very well, Yasmin. Good to see you, by the way. It's been a long time. So 3 times 1 here gives us 3. We have x to the power 2 plus x to the power 0 minus 6x minus that 0. And then finally, we can write this as 3x squared. Now, if you remember anything about variables raised to a certain exponent, for instance, 0 here, x to the power 0 will give us 1. No, 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 not even. Why would I ignore you? Not a chance, eh? Not a chance. Not a chance, Yasmin. Definitely wouldn't ignore you. Just obviously like doing intense focus here on what I'm doing. Otherwise, definitely not ignoring you. I hope you're well, by the way. It's been a long time. Okay, so the final answer that we have there for deriving this particular expression, x minus 3 into x squared plus 1, we get 3x squared plus 1 minus 6x. Man, this morning there's a lot of activity here. Huh? A lot of people with a lot of stuff happening. All right. Okay, so let's look at this one. So once again, we are finding the derivative. Yeah, I've been scarce on this platform for quite some time, but yeah, it's just that time of the year. A lot of a lot of writing happening. Kids preparing for exams, adults preparing for exams. Rewrites happening in this part of the country where I'm at. So just trying to help out there. Okay, so we are deriving here. We are also deriving. We're gonna find the derivative with respect to x for this particular expression. So obviously, what we're going to first do before we even apply the power rule is that, or derive, we are going to simplify this expression. So what we can see here is minus 2x. There's a bracket. X minus 1 is raised to the power 2. So here what we want to do first is we want to simplify this expression, because before we derive, we have to simplify a given expression. Whilst we are busy simplifying, this notation says we are going to stay with the expression whilst we are busy simplifying until we are ready to derive. So we are going to simplify this. So we are going to think of what? Bed mass, brackets, exponents. So if we look at this, there's brackets. Brackets mean multiply. So negative 2x and this bracket have a relationship of multiplication. This exponent is 2, and there's an x minus 1 in brackets raised to the power 2. So we are going to actually expand this out. So what we're going to do, we're going to write minus 2x, x minus 1 into another x minus 1. Well, good night. Have a good night's rest then, Yasmin. It was really nice seeing you again after a very long time. Hopefully when I'm not teaching mathematics or something like that, we'll definitely have a chat, that's for sure. Okay, right. Then what we are going to do is we are going to, according to our grade 9 method, we are going to distribute. Distributive law. We are going to multiply x and x. Take the same x, multiply x and negative 1. Okay. Take negative 1 times x. Take negative 1 times negative 1. All right. Okay, then the negative 2x, we are going to follow it up the minute we are done with multiplying out this using our method that I've just explained. So x times x. So let's take this negative 2x, make it wait for a little while. You know, negative 2x is a gentleman. It waits so that these two brackets can actually be multiplied out. So x times x is x squared. X times negative x, remember this is a positive times a negative, we get a negative. A 1 times 1, we still get 1, and then the x. Okay, remember there's a 1 there, even though it's invisible. That is the coefficient of the x value here, the x variable. Then we take negative 1 times x, negative times a positive is also a negative. 1 times 1 is 1, and then the x there, so another negative x. Then negative 1 times negative 1, we get a positive 1. Okay, so far so good. So negative 2x patiently waits its turn. So we just need to add the like terms there. So x squared minus 2x plus 1 is what we get inside there. Say d over dx. Then we distribute the negative 2x inside the bracket for all 3 terms, because the distributive law is a law learned in earlier grades, and we just utilize it all the way. So negative 2x times x squared we multiply the sign, the number, the letter. The sign, the number, the letter. So negative times a positive gives us a negative. 2 times 1, there's an invisible 1 there, is 2. Then x times x squared. According to the laws of exponents, if you'll remember that whenever we are multiplying same bases, we keep the base and then we add the exponent. So x to the power 1 is there. So x to the power 1 times x to the power 2 gives us x to the power 3. Do the same thing. Negative 2x times negative 2x. Negative times a negative, positive. 2 times 2 is 4. X times x, x squared. And then we say negative 2x times the positive 1. Negative times a positive, that's a negative. 2 times 1 is 2. And then the x right there, spot on. The d over dx. We have been awaiting for the moment where we have separate terms like this. Now we are ready to do what? To derive. What happens when we are ready to derive? Since this d over dx is attached, has been attached to the expression inside the bracket, when we are ready to derive, then the d over dx does what? It disappears. It pulls a disappearing act. Then we derive each individual term using the power rule. And the power rule simply says this: the exponent that is there, it descends, gets multiplied with the current coefficient. So negative times the 3 is negative 3. We multiply that with the current coefficient 2, x 3 minus 1. So we always subtract 1 from the current exponent. Same thing here. 2 descends, gets multiplied to the current coefficient 4, x, then we say minus 1 to the current exponent. Do the same thing with negative 2x. Negative, there's an exponent 1, so obviously that negative 2 times the 1, x, 1 minus 1. We are always subtracting 1 when we are deriving each individual term using the power rule. Then simplify. Negative 3 times 2 gets negative 6. X, what's 3 times 1? It's 2. 2 times 4 is 8. X minus 2 times 1. Maybe you're going to say 2 minus 1. What happened to the 1? The 1 is there, guys. Okay, it's there. It's there, but invisible. Okay, negative 2 times 1, negative 2x to the power 0. Then, guys, remember that anything raised to the power 0 gives us 1. So when we finally write the final answer, we get negative 6x squared plus 8x minus 2. Remember, it's 2 times the x here. The 2 and the x have a multiplication relationship. So x to the power 0 is 1. 2 times 1 gives us 2. So that's our final answer. We've just derived this expression simply by simplifying, using our expansion, foiling it out, and then ultimately finding the derivative of each individual term. Okay, not too shabby here. Not too shabby at all. Okay, the next question says we need to find f prime of x if f of x is equal to x plus 1 over root x, the whole thing squared like this. So we need to find f prime x. So once again, this is notation for finding the derivative. This is just different notation. F prime x. It still means we need to find the derivative of which function? This function. So now, since we are given this in this notation, right? Remember, for these ones, dx, d over dx, I said that whenever we are ready to derive this particular notation, it disappears. When you are ready to derive, it disappears. So for instance, you guys saw that I would simplify what's inside the bracket until I'm ready to derive. When I'm ready to derive, I see I have my individual terms, that this dx disappears, and then what do? I apply the derivative. I apply the power rule, which allows me to derive to each individual term. So this is the case for dx with an attachment, d over dx with an attachment. What happens is I simplify, retaining the notation until I'm ready to derive. Then when I'm ready to derive, I have my individual terms. Then you see this disappearing. Now, what happens with this notation? We have f prime x. If f of x is equal to, there's my expression. So what I do here, I'm going to write f of x what f of x is, guys, is simply functional notation, but it stands for y. All right. So here, this is my expression for the function. So f of x is equal to this. So what I'm going to do is I'm going to simplify this. All right. F of x is equal to, so x plus 1 over root x, the whole thing squared, means what? I need to open two brackets of x plus 1 over root x. And then what do I do? I'm going to use my distributive law. In grade 10, they knew this as FOIL. You're in grade 12, now that you're in grade 12, you're just applying your methods used in earlier grades. So x times x gives you x squared. What's the goal of doing all of this? I want to get separate terms, so that when I have separate terms, I can then derive each individual term using the power rule. That's what we're doing here. So x times x is x squared. X times 1 over root x, that gives us x over root x. Then 1 over root x times x gives us another plus x over root x, plus 1 times 1 gives you 1, root x times root x gives you root x, the whole thing squared. So I'm going to obviously simplify all of these, okay? So now this is x squared. This x over root x, something to note here, you can write this as x over this root x. Change the root into exponential form. Root x can be written as x to the power half. Now someone will be asking how. Well, in grade 11, you guys learned how to change roots into exponents, okay? And the thing basically went like this. X to the power m over n can be written as x to the power m, the nth root. This denominator exponent for your rational exponent, this belongs here. The m is the current exponent. Okay, all right. Hami, you are asking, how did I get x over root x? Okay, this goes back to this. What's x times 1 over root x? So as I'm doing this, I'm multiplying x times x, x squared. X times 1 over root x. What's x times 1 over root x? So here it is, x times 1 over root x. This x is an x that's like, you can write it as x over 1 times this 1 over root x. This is in the numerator, this is in the denominator. So what you do when you multiply is say x times 1, that gives you x. 1 times root x in the denominator gives you root x. So that's how I got my x over root x. So x times x, x squared. X times 1 over root x. This x is in the numerator, this one is in the denominator. So that's why it's x over root x. You multiply these two, same thing. This one is in the denominator, this one is in the numerator, x over root x. Then 1 over root x times 1 over root x gives you 1 over. The thing is, this root x times root x is root x, the whole thing what? Squared. Okay, now I'm saying that x over root x, you change this root x into exponential form, x to the power half. X over this root x, you can write as x to the power half, plus now 1 over root x squared. Obviously the square root and the square, what do? They cancel each other out. So I'm left with x. Okay, maybe someone who does not understand, guys, if you have x, this root x, you can write it as x to the power half to the power 2. So if you look at this, half times 2, what's half times 2? A half times 2 gives you 1. So that's why you get x as your answer. So if you look at it in the sense of changing this root to exponential form, it's x to the power half. The whole thing squared means you're multiplying the half and the 2, because there's a law of exponents that says whenever you have a base raised to a certain exponent raised to another exponent, what you simply do is you multiply the exponents. So this becomes m times n. All right, so same thing here. Half times 2 gives me x to the power 1. X to the power 1 is x. Okay, so that's where that comes from. Now here's something else to note. X divided by half. X divided by x to the power half. All right. Trienta for, I've just started out this thing, so yeah, I just decided to do a random live. It's not like I'm doing it weekly or anything like that. So there's nothing officially formal yet. This is just, like I said, it's very random. Yeah, on this account. So x divided by x to the power half. All right, so what we can do here is we know that whenever we are dividing same bases, there's the law of exponents that says when you are dividing same bases, what you do is you keep that particular variable base, which is the same, and then you can subtract the exponents. That's a law that you learned in grade 9 and in grade 8. So here, what we do is we say x to the power, there's a 1 exponent there, so we say 1 minus half plus x to the power. Same thing here, 1 minus half plus 1 over x. Okay, so I'm just drawing it out, but basically any grade 12 student would know this. All right, hopefully, that if you are dividing same bases, you keep the base for each variable, which is the same, and then you subtract the exponents. So all you simply do, you take your calculator and you ask yourself, what's 1 minus a half? So 1 minus half is simply equal to, so we have x squared plus 1 minus half, x to the power a half, plus x to the power a half, plus. Now, remember I said all variables need to be in the numerator. So here's another law that you should have learned in earlier grades, and that is if an exponent is raised to a negative, this can be written as, if a variable is raised to a negative exponent, you can rewrite this with a positive exponent by doing the following. The current variable is in the numerator, if you think about it, all right, and it's raised to a negative exponent. But what happens is that if a variable is raised to a negative exponent, the variable changes position. It goes to the denominator. The exponent that is negative changes from negative to positive. And then the coefficient that was left there is 1. So you leave that 1 there. This 1 that is in the denominator is obviously there, just unseen. So the answer is 1 over x to the power n. You can write this 1 over x to the power n, vice versa. You can actually say 1 over x to the power n is equal to, you can take this variable, write it in the numerator. What happens to its exponent? It changes from positive to negative. So in the same vein, we have 1 over x here. We can write this as x to the power negative 1. Okay. Why did we just do that? It's because, like I said when I started off this lesson, I said all variables, for instance, variables, if you are going to derive and there's a variable that you are deriving with respect to, that variable you derive must be in the numerator. The current variable that you want to derive with respect to is in the denominator. So what you do is you apply the exponential definition that you learned in grade 9, and you change this 1 over x to x to the power negative 1. 1, 2, 3, 4 terms. These ones are like terms. Why? Because the variables and their exponents are the same. So I'm going to add these like terms. It's plus 2x to the power half, because whenever you are adding like terms, you keep the variable and their respective exponent, you add the coefficients. So this is a 1, there's a 1 here, 1 plus 1 gives you, beautiful, 2. So you have 2x to the power half plus x to the power negative 1. Guys, I would say now we have 3 separate terms. We are ready to derive all of our terms. Variables are in the numerator. The roots have been changed to exponential form. There are 3 separate terms. Now we are ready to derive. Remember, we are asked to derive f prime x if f of x is equal to that. So f of x, we dealt with f of x. F of x is now fully simplified. We are ready to derive. When we are ready to derive, this notation comes into effect. We now say f prime x. And then what do? We derive using the power rule each individual term. So this x squared becomes 2x 2 minus 1 plus this half comes down, gets multiplied with a 2. So we have 2 times a half, x to the power half minus 1. This term, who comes down? Negative 1 comes down, gets multiplied to the current coefficient, which is positive 1. Then we say x to the power negative 1 minus 1. Remember, we're always subtracting 1 from the current exponent, subtracting 1 from the current exponent, subtracting 1 from the current exponent. This exponent becomes the coefficient that we multiply the current coefficient. This exponent becomes the coefficient that we multiply with the current coefficient. This exponent becomes the coefficient that we multiply with the current coefficient. But we are always then subtracting 1 from each exponent. That is the power rule. That shows that we are deriving. So that's why I said to you guys that whenever this notation is what we are asked to derive, this always appears when we are ready to derive. When we are ready to derive, f prime x appears. When we are ready to derive, if they said y prime appears. If we are ready to derive dy over dx, they will appear when we derive. So when we are deriving, these appear. Okay, and then final answer, 2x, because 2 minus 1 is 1. That 1 invisible, it's there, plus 2 times a half is 1. X, half minus 1. Surely you know that's negative. You can take your calculator, you'll get a negative half. And then positive times a negative gives us negative what? Negative 1x. That negative 1 minus 1 gives us negative 2. Then, guys, we need to make sure that when we write our answer, we do not leave our answer having negative exponents. So, final answer, 2x is fine, plus that 1 will always be there whether we write it or we don't if there's a variable there. So x, all right, 1 over x to the power positive half. What happened there? Look, you remember I said we can't write our answer having a negative exponent. So therefore our numerator is 1. The x goes to the denominator. Its exponent changes from negative to positive. Remember this law. Okay, this definition of exponents learned in grade 9. Okay, minus, once again, this one as well, it's going to be 1 over, this x goes to the denominator. The exponent changes from negative to positive. Then finally, guys, what we can then do is we can say 1 over this x squared. We can change that exponential form to root form, 1 over x squared. Derived. That was f prime x. Okay, right? So if you can see that this deriving in calculus grade 12, guys, finding the derivative simply requires us to have a lot of foundational knowledge from earlier grades. If that foundational knowledge for earlier grades, our exponents, you know, your grade 9 and your grade 10 exponential knowledge, grade 10, 11 is not up to scratch, what you are going to find, you're going to find yourself having a bit of difficulties. Okay, yeah, so it's very important that you make sure that you are applying this consistently. Trienta, thank you for so much. I see your comment there. No, please get used to it, my brother. I understand you better than my grade 12 maths teacher. I think most students will say that, right? I'll tell you this, and that is that I think a prophet has no honor in his home country. Baby boy, yes, definitely, you must leave your answer in positive exponents. Definitely, please, right? Yeah, because you learned that in earlier grades that you do not leave a final answer when simplifying. You don't leave a final answer having what? Negative exponents. So it's necessary, baby boy. Okay, it's necessary. Trianta, I was just going to say that even my kids at school probably tell you the same thing. Prophet has no honor in his own home country. You are so used to your teacher, but you will get so nicely used to someone else that's a complete stranger. You know, I don't mean that in a bad way, but it just is what it is. I think that's just life in general. Y is equal to, so let's do, I think, 2 more. Now check this one out. Please take note, guys, of the notation. The notation this time. So we are being asked to find the derivative. Okay. Where the subject of the equation should be y, because this here says that the subject of the equation should be y. So we must check if our equation has the subject y. Does it? Yes, it does. And now we are deriving with respect to what? With respect to x. So it is x that we need to derive with respect to. Okay, I'm explaining this deliberately because sometimes in a question they'll say maybe dA over dt. You must understand what that means. If they say dA over dt, that means A must be the subject of whatever equation you have. Secondly, if they are saying dt, then it means you need to derive with respect to t. Okay, yeah. So we know that x is the famous variable that's used, but yeah. So you just understand that these are the situations that we are finding ourselves in. Okay, so very, very important. Baby boy, I would really encourage you to ask your teacher. It's just that I'm actually like, I have a set of questions that I need to do here, all right? And I need to do them before 6:30 because I'm ending the live at 6:30. So the question that you've asked, I'm not doing first principles, I'm doing differentiation rules, all right? And this is also so that I can actually save this and put it up online so that people can rewatch it at their own time. So I need consistency in what I'm doing in the live session. Maybe at another time, but I think you have access to your teacher. Please do ask your teacher today. You're going to school, right? So you should ask your teacher to do it. That would be amazing. And yeah, dy over dx if y is equal to. So this is the sort of notation where, as I had said, we are actually going to take the equation as it is and we are going to simplify the equation. You know what I mean? We are going to simplify this expression whilst y is there. When we are ready to derive, dy over dx will appear. So this is part of the appearing notations. Dy over dx, y prime and f prime x, they appear when we are ready to derive. You remember this one? We took f of x, we simplified. After we're ready, we done simplifying, we have separate terms. Then we derive. F prime x appears. Dy over dx will only appear after simplification has happened with the particular equation, right? Yeah, so these ones are the ones that appear. So let's first simplify. So you can see here, guys, that two brackets again. So we need to do Mr. Foil. X times x, x squared. X times 1 over x. Remember, this x is positive, this negative. This 1 over x is negative. So positive times a negative, negative. X times 1 over x. Now, guys, this is supposed to be x over x. But x over x, guys, is actually equal to what? To 1. So it's like this x is in the numerator, this x is in the denominator. These two cancel out, all right? Because x divided by x is 1. So I'm going to write negative 1. Then here, 1 over x times x. Once again, this is in the numerator, this is in the denominator. You multiply these two, you get positive 1, because a positive times a positive is a positive. 1 over x times x is equal to 1. Then 1 over x times negative 1 over x. What's a positive times a negative? It's a negative. What's 1 times 1? It's 1. What's x times x in the denominator? It's x squared. Okay, I think we are getting separate terms onto here. Next step, x squared. What's minus 1 plus 1? That's 0. So that's nothing there. 1 over x squared. What's short now? What's short is that this x 1 over x squared term, we need to write it in such a way that the variable x is not in the denominator. We want to not have the variable x in the denominator. So what are we going to use to help us out with that? We are going to change this, all right, using our exponential definition to what, guys? What are we going to change it to? We are going to change it to, so it's going to be x squared minus x to the power negative 2. Do you see why I did that, guys? This is all in the name of making sure that my variables are in the numerator, okay? Because I want to derive these individual terms, but my x must be in the numerator. I can't have an x in the denominator because I'm deriving with respect to x. X is in the denominator. Can't have that happening. So I use my exponential laws. See the exponential law that I'm using here? Hey, the definition. And you thought grade 9 would not feature in grade 12. Guys, must know our stuff. It's so important to know our stuff. The earlier grades, the concepts covered in earlier grades are very critical. Now we are ready to derive. So what do? dy over dx appears. Why? Because we are ready to derive, and we say equal to. Then we apply the power rule. 2 gets multiplied. Current coefficient 1. 2 times 1, 2. X, then we say 2 minus 1. Minus negative 1 current coefficient. Multiplied by what? By negative 2. X to the power negative 2 minus 1. Okay, then let's go. Finally, we get 2x. 2 minus 1 is 1. Negative times the negative is positive 2x to the power negative 3. But do we want our final answer having negative exponents, my beautiful good people? Icon. So we write 2x plus 2 over x to the power 3. Done and dusted. That is dy over dx. Finished. Capush. Finito. Right? Not too shabby, ne? Not too shabby. Not too shabby. Okay. So do you see the guys that need to appear? F prime x appears when we have simplified, we are ready to derive. Dy over dx also appears. If we are asked to derive dy over dx, if y is equal to, we work this y until we have separate terms. When we are ready to derive, dy over dx appears. But remember, I said with this notation, dx and d over dx, what happens to them? If you are given a question, there's dx into the brackets, you simplify whilst dx is there. Once you get separate terms and you are ready to derive, then the dx disappears. You see, you just write equal, dx disappears. Thank you, Salman, for the rose. Wow, my first rose for the day. First gift for the day. Thank you. Then this one as well, d over dx. We keep d over dx there until we are ready. We simplify, simplify, simplify. When we are ready to derive, finally we have separate terms. Then what do? D over dx disappears. So you must know the ones that disappear. This is the notation that disappears when you are ready to derive. It stays there until we are ready to derive. It disappears when we are ready to derive. This one, dy over dx, y prime and f prime x, they appear when you derive. All right. Okay, let's look at the others. Okay, let's look at the others. This one said we need to find h prime x. If h of x is equal to, let's just write down the question, negative x squared plus 3x plus 4 over 2x plus 2. Okay, we need to get what? H prime x. But remember, that's the notation that will only appear when we are ready to derive. So we take this function as it is, and we first try and simplify it. You can see this is in grade 9. If I asked my grade 9 learners and I asked them how many terms are in the expression, my grade 9s would comfortably say there's one term in the expression. Why? Because a fraction is always one term. So what this means is that we need to simplify this, right? So we look at the numerator, we look at the denominator, and we can see that there are how many terms in the numerator? There are 3 terms. In the denominator, there are 2 terms because the plus and the minus sign separates terms. So since there are 3 terms, there are 2 terms here. What we're going to do is we are going to look at factorizing the numerator and the denominator. Grade 10, you looked at a trinomial over a binomial and how you simplify that. You look at how you can factorize numerator and the denominator. So what we do here, in the numerator, it's negative x squared plus 3x plus 4. So if we are going to factorize, we are going to take out the highest common factor. Okay, so whenever a first term, the variable with the highest exponent has a negative, we take out that negative sign as the highest common factor. Then we have x squared, changes everything inside, negative x minus 4 over If we look at the denominator, what's the highest common factor? 2 is the highest common factor. That leaves us with x plus 1. Okay, hopefully we know how to factorize, guys. I've just factorized the top. I've factorized the bottom using highest common factor factorization, taking out the highest common factor. Secondly, can factorize this in brackets because this is a quadratic trinomial expression. I can factorize it by opening two beautiful brackets. X squared I can write as x and x. Then I want to find the factors of 4. When I multiply these factors of 4, I need to get -4. When I add those same factors, when I add them together, I need to get the coefficient -3, right? So the two factors of -4, which when I multiply give me -4, but when I add them give me -3. That is my 4 and 1, where my 4 is negative and my 1 is positive. Let's just check quickly. What's -4 times 1? It gives us -4. What's -4 plus 1? It gives me -3. So when I add these, I need to get the coefficient of the middle term. When I multiply them, I need to get the constant term. Okay, so it's very important, that thing. Zaza, I do just contact me, check me out there in the inbox. You can just send me details, but of course, yeah, that comes with you know what I mean. And I can help your daughter out. I can help your daughter out through you, assisting her. Get my contact details, and I can consistently assist. But like I said, it's there's a price to it, so just contact me in the inbox. We can chat about it, okay, and we can negotiate. So x plus 1, so we have negative into x minus 4. This is grade 12 Zaza, but grade 8 definitely. Grade 8 is a very interesting grade, but yeah, it's also nice. I think this just need to adapt there to the content. Okay, so x minus into x minus 4 into x plus 1, that's factorized over 2 into x plus 1. Now guys, when I'm at this stage, because factorization has happened in the numerator, there's factorization in the denominator, I ask myself again, how many terms in the numerator? There's 1. How many terms in the denominator? There's 1. What makes it 1? The brackets makes it one term. Now cancellation can happen nicely, okay, because x plus 1 divided by x plus 1 gives you 1. Does that make sense? Okay, then what you are left with here then is minus into x minus 4 over what? Over 2. Okay, and then look at this. Minus, put the x back, minus x plus 4 over 2. Then in grade 8, you guys learned that when you have two terms and you have 1 at the numerator, in the denominator, you can actually split these. Okay, and then you have now what we refer to as two separate terms. Negative x over 2. Now I can actually write this as negative half, the x as the coefficient, as the variable. So this is negative half. That's my coefficient. Then the x is a variable in line with the divide sign. Plus, what's 4 over 2? 4 divided by 2 is 2. Guys, you see now, as a grade 12 learner, it becomes so important for me to know how to simplify as per my grade 10, 9, and 8 syllabus, the things that I learned in earlier grades. That's why calculus is such a pain when learners in grade 12 don't know the basics in the earlier grades. Okay, that's the problem. Okay, so it becomes very, very important then. Very, very important. So yeah, ESCO RSA. What's always funny is my spectators in the comment section explain to the kids why the signs changed when you brackets, bro. When you removed the brackets, why did the sign change when I removed the brackets? Okay, remember these are grade 12 learners I'm talking to, ESCO. So you are asking me to explain to grade 12 learners why the signs changed. Okay, so it's just that me, I'm thinking that I'm speaking to people that know, but let's do that. So this negative, when you distribute it to the x, negative times x is negative x. Negative times negative 4 becomes positive 4 because we are applying the distributive law, okay, as per your grade 8 syllabus. Grade 8 syllabus, you learned the distributive law. Grade 9, you learned the distributive law. 10, it was there when you did expansion. 11, you utilized it in some problems. In 12, you should be affluent in it, okay? So negative x plus 4. Then there's a 2 in the denominator. So you can write this as negative x over 2, split it, plus 4 over 2, split it. Then 4 divided by 2 is 2. Negative x over 2 you can write as negative half, the coefficient, with the x variable. That is h of x. Are we ready to derive now? Definitely. Why? Because we have two separate terms. The power rule can be applied to terms that are separate. So now we say h prime x, because that's what they wanted us to find. We now introduce the, so how did we get negative half? The coefficient. So if I asked a typical grade 8 learner, because grade 8s are doing algebraic expressions in term 2 now, okay, so very true, Esco, you are not wrong, you are very right. A lot of grade 12s, they miss the basics. You would think that they know, but they don't. So it's very important. So thank you for that comment. It really helped so that I can explain that particular thing, that I did there. So so the question was, how did you get negative half? So Hami, you have, like I said, negative x plus 4 over 2, right? So what I said is that this negative x plus 4, there's 2 terms in the numerator, there's 1 in the denominator. So we can split the negative x plus the 4 to become negative x over 2, the 1 denominator. This only happens when there's 1 denominator, guys. 1 term in the denominator, you have many terms in the numerator. You can write these as individual terms split as a fraction with that same denominator. So negative x over 2 plus 4 over 2. Now, the numerical number coefficient. By coefficient, guys, I mean the number that stands before the x. So there's an invisible one here. I want to say this. Guys, maths makes me believe in God that much more. There are things that are unseen in mathematics that are sometimes not written, but they are there, they are presence. They have a presence, and sometimes when we make them appear, it's like, wow, I didn't know that was there. So for instance, the x, there's a coefficient of 1 that's there, you see. And then in the denominator, you have 2. So if I asked you, what is the numerical coefficient for x? Then if you make the 1 appear, there it is. It's negative 1 over what? Over 2. This variable x is in the numerator. I just simply write it as x, the variable. So I have my coefficient, negative half, which I'm basically distinctly writing, and then my variable x, which is there. Okay, so that's where I got the negative half from. I hope that makes sense to you, Hami. Please let me know in the comment section if it makes sense. If it doesn't still, then I don't know how I can explain it even better. But yeah, in the numerator, there's a negative 1. In the denominator, there's a 2. So this negative 1 over 2 gives me the fraction negative a half. This variable x is in the numerator, but I just want to distinguish between my numerical coefficient, which is a fraction, and my variable, all right, which is the single term that I have, which is my first term. And then after that, I have 4 divided by 2, which is 2. Am I ready to derive? Yes. I derive now with respect to x. Now, if I derive my first term, I apply the power rule. Then it means the exponent 1 that was there gets multiplied with the current coefficient. So it's a negative half times the 1, x1 minus 1, because I'm always subtracting 1 from the exponent. The derivative, guys, of a constant is 0. Okay, derivative of a constant is 0. I remember actually yesterday one of my learners asked me, why do I say the derivative of a constant is 0, right? And I explained that sort of like y, but again, hopefully we all understand that derivative of a constant is 0. So our final answer is a negative half x to the power 0. But remember guys, anything raised to the power 0 is actually equal to a base of raised to the power 0 is equal to 1, except when a cannot be 0, because 0 to the power 0 is not 1. A to the power 0 in this case is equal to 1. So x to the power 0 is 1. So we have negative half, but the relationship of x to the power 0 with half is multiply. So obviously that's negative half times 1, which is a negative half. That is the derivative of this guy. It's a half, negative half. Okay, maybe lengthy explanation, but I hope there's clarity. And yeah, the maths keeps on mathsing. Okay, just want to do 2 more and then I will leave you to your devices. Here's another question. They want y prime if y is equal to, and the expression is x cubed plus 8 over x plus 2. X cubed plus 8 over x plus 2. Now, y prime. Remember, this y prime falls under the category of notation where y prime will only appear when I'm ready to derive. So, as I need to still first simplify, y prime is not going to appear. So for now, we say y is equal to x cubed plus 8 over x plus 2. Hey, guys, look at grade 10 creeping up on people. You look at this expression, x cubed plus 8. You look at this one, x plus 2. X cubed plus 8. If you look at this, when they would say simplify in grade 10, this thing, you would know how to simplify it when you are in grade 10. Because in grade 10, you learned about cubic factorization. The denominator x plus 2, 2 terms. So in the numerator, 2 terms. In the denominator, 2 terms. This numerator can be factorized. We can factorize this numerator of 2 terms. This one cannot be factorized. Okay, so we have x to the power 3 plus 8. We open a binomial bracket. We open a trinomial bracket. Since there's a plus there, we write a plus in the binomial bracket. Then we follow it up with minus plus. Now, some of you are probably like, And me, I'm like, yeah. Because remember in grade 10, when you dealt with cubic factorization, okay? When you dealt with cubic factorization, I'm going to write the same question, but this time around, instead of writing x cubed plus 8, I'm going to write x cubed minus 8. Okay, I just want to get the signs out of the way, because it's always nice to know what the signs will be. So if there's a plus, guys, and when I say cubes, remember, x to the power 3 is a cube, and then 8 is also cubic in nature. How? In other words, if I'm going to say what is the cube root of x cubed, do you know what I get? I get x. What is the cube root of 8? The cube root of 8 is 2. All right. So that's why I say this is a sum of 2 cubes. In grade 10, you learned how to factorize the sum of 2 cubes, and you also learned how to factorize the difference of 2 cubes. That's what you learned in grade 8. And what you learned is that you open 2 brackets. One, that's a binomial bracket, meaning there's 2 terms in it. And then the other has 3 terms in it, a trinomial bracket. That's what you learned in grade 10. Then what would you do? If there's a plus here, then you finish the first bracket with plus. If there's a minus there, you finish the first bracket with a minus. So that explains the plus sign for the first binomial bracket if there was a plus sign in the cubic expression. And then that explains the minus sign in the first bracket if there's a minus sign for your cubic expression. Now, guys, for plus, you follow it with minus plus in the binomial bracket. But if you had minus, you just follow it with plus plus. Okay, now I know some of you are like, memorization. Well, of course, definitely memorization. Okay, then what is the cube root of x cubed? Cube root. Because it's cubic factorization, because it's cubic, we use the cube root of each term. The cube root of x cubed, you saw most, it's x. X. Cube root of 8, 2. 2. All right? Then you square the first term to get the first term in the trinomial bracket. In other words, you ask yourself, x times what gives you x cubed? Obviously, if you square it, you also get the answer. You square the first term, you get x squared. 2 times what gives you 8? That's 4. Are we together, guys? So in other words, that's the same thing you'd be doing here. X times what gives you x cubed? The x squared. 2 times what gives you 8? The 4. And then obviously the sign negative times a positive gives you that negative sign. A positive times that positive gives you that positive sign. Then the interesting part is getting the middle term. So the signs are already placed for you, but how do we get the middle term, guys? The middle term is simply this. You just take this 2 and this x as they are. Okay, sorry guys, something came up or something popped up on my screen. So you multiply these two together, you know, just don't even consider the sign. You just multiply these two. We multiply x and 2, we get 2x. We multiply x and 2, we get 2x. Okay, that's, yeah, factorization is done, guys. So that's how we factorize that. So I'm just gonna rewrite this. So in other words, factorizing x cubed plus 8 would mean we open 2 brackets, as I said. That's a bracket of x plus 2 and another bracket of x squared minus 2x plus 4. All over what? All over x plus 2. Now, do you see where I'm at now? Now, cancellation can happen because x plus 2 divided by x plus 2, I can cancel because it's not a cross an addition or a subtraction sign. One term in my numerator, one term in my denominator. Cancellation can freely happen. What am I left with? I'm left with x squared minus 2x plus 4. Do you see? Now I'm ready to derive. Simply ready to derive. Nicely, simply, easily ready to derive. Because I factorized, simplified by factorization. When I'm ready to derive, remember I was asked to find y prime, then I say y prime, it appears equal to, then I apply my power rule to each individual term. So this is simply going to be 2x, 2 minus 1, minus 2x, 1 minus 1. Derivative of a constant is 0. Then final answer, I get 2x minus 2. Because remember, this would be x to the power 0, which gives me 2x minus 2. That's y prime, guys. Prime time. Prime time. Right? Not too shabby, hey Nige? I hope it's not too shabby, guys. Not too shabby. I think I have time just for one more. I'll literally do one more, guys. One more that is a bit unconventional. I think let me just do one more that is a bit unconventional. Okay, and by unconventional, I just mean that maybe you'd be like, huh? And then... Okay, so let me just for the purpose of those people that are, there are people that are screen grabbers. I've found that when I do live sessions, there's people that are screen grabbers. They grab the screen and yeah, so, and that is for those screen grabbers. You know, I'm sorry if the light is not that great, but yeah, that's for the screen grabbers, you know, the grabbers of the screen, the grade 12 screen grabbers. Yeah. Okay. I just want to do one more and then I'll leave you in peace. Because I need to live in peace as well. Hopefully I'm not left in pieces. So dm pm cubed q squared m squared plus r squared. Okay, very interesting this one. Right, I just want to explain something here. So here, this is dm, abo. X ukay. Maybe people are asking, X ukay? X uyephi? X uphi? Var is X. Well, you know what, guys? We are now being asked to derive with respect to which variable? With respect to m. So that means we're now going to look at our expression. Remember, we always first make sure we simplify. But you can see this is already simplified. We have 1, 2, 3 terms. They are separated by a minus and a plus sign. So there's no further simplification that needs to happen. So that means we are ready to derive. Now remember, since this is dm, meaning derivative, derive with respect to m, and it's attached to this bracket, remember the minute we have simplified and we are ready to derive, this dm falls away. But we just need to be reminded, which variable are we being asked to derive with respect to? We need to derive with respect to m. And this is the what you might call it's the thing that we need to be aware of when we are deriving. Please, guys, always take note of the letter. Okay, this here means we are deriving the function with respect to x. Okay, so this tells us which variable we need to be deriving with respect to. Here, the denominator tells us which variable we need to be deriving with respect to. Here, y must be the subject for that particular function, but we are deriving with respect to x. Okay, so the denominator is always the one telling us. If you have denominators, if you have this letter with respect to the letter, right? So for instance, look at this question. And this is dA over dr. So here we are being told that in whatever this function that you have or equation, a is supposed to be the subject, which it is. Right? If it wasn't, we would first make a the subject of the formula. Another grade 10 concept, literal equations in grade 10, making a particular equation, making a variable the subject of a particular formula. Guys, those are all concepts in grade 10. Grade 10 is coming with a bang in grade 12. dm, right here, for instance, dm, so there's a bracket. These are where we have to first check. Okay, this is a question that I'm looking at, but look at these questions, these ones. Okay, these ones, dk, we need to derive with respect to k. You see, so we must always check here, derive with respect to x. You know, there's q and there's r, but we're deriving with respect to x here. Here we need to derive with respect to r. So our variable of focus is m. So here now we can see that we are ready to derive. The terms are separate. So we are ready to derive. So that means P, Q, and R we treat them as constants. We treat them as constant. We treat the other variables that we are not being asked to derive with respect to as constants. You know, p we treat it as a constant, q we treat it as a constant, r squared we treat it as a constant. You see, yeah, it's like a numerical value. You know, because remember, variables stand in the place of something that we don't know. But now, because we are deriving with respect to m, that is our main variable we are deriving with respect to. So look, when I apply the power rule, what happens? Remember I said, since we are focusing on the m, we go to the m. That is the main variable we are deriving with respect to. There's a 3, so that means we bring down the 3, gets multiplied with the coefficient p, m3 minus 1. Do you see why I'm doing that? Because I'm deriving with respect to m. Look at this one. Negative q squared, I treat it as a coefficient. Negative q squared, we times it by the what? By the 2. 2 comes down, gets multiplied with the coefficient. m2 minus 1. You see, guys, because I'm deriving with respect to m. That's why I'm doing this. Okay? There's no x. We were asked to derive with respect to m. Okay? Imagine if there was no dm here and they said dp. Then it means if they said derivative, I need to derive with respect to p, it means I would treat p as the main variable. Everything else would be a numerical value or a coefficient or a constant. You see? So that's what's important here. Please take note What letter are they asking you to derive with respect to? R squared, a constant, derivative of a constant is 0. Do you see that, guys? So what I'm saying here is that we treat other variables, if there are any other variables, as if they are constant. Okay. Hami, remember, what did I say? The reason why 2 is in brackets, it's like I could have put even this 3 in brackets if I wanted to. Okay. It's just that I'm trying to show you that I am multiplying. Remember, I take the exponent 2, I multiply it with the current coefficient, which is 2 squared. So it's 2 squared times 2. So I'm just utilizing brackets. Remember, guys, for multiplication, you can use brackets, you can use a dot, you can use multiply. These all mean multiply, all of them. Okay, so don't be shocked if you see maybe sometimes I'll say 2 squared times 2, I'll put a dot or put multiply or put brackets, because I understand, mathematically speaking, all these 3 things, they mean multiply. Okay, I hope you are with me now, Hami. All right. So when you finish off, this is 3pm squared minus 2q squared m. That is my derivative with respect to m. Okay. You could put it in front of q. Okay. Remember this thing, Hami. In maths, with multiplication, a times b is equal to b times a. We say multiplication. This is a grade 8 concept. Multiplication is commutative. In other words, whether it's b times a or a times b, Hami, it's the same thing. Okay, 3 times 4 is equal to 4 times 3. Do you agree, Hami? Okay, multiplication is commutative. So if you put the 2 before or after, doesn't matter. Okay, because multiplication is commutative. This is a grade 8 concept. In fact, grade 7, right? You learned that multiplication is commutative. Okay. The other thing that's commutative is addition. Okay. Addition and multiplication are commutative. In other words, the order in which you place things doesn't matter when you are multiplying and when you are adding. Subtraction and division are the ones that are not commutative. Okay. So here's something new for you if you didn't know before. All right. So I hope you are well, Hami. I hope that you are hammering it in. Okay. Hami, hammy, 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 hum, ham. Hammering it in. Hammer in the mat, Hami. Okay. Okay, guys, I'm gonna love and leave you. Thank you so much. That was amazing. So DM disappeared when I derived because I have separate terms. Okay, I hope you guys learned something today. Yeah, hammer it in, Hami. Okay, thank you so much for joining. Really appreciate it. Trienta, thank you so much. Continue fighting your battles by praying. You know, God will continue to be your shield and protector. I guess you joined in the live because he's very much aware of you. So I hope you enjoyed that. And thanks for the generous comments there. I saw your comments in the comment section. I really appreciate it. And to all that joined in, it was really nice having you guys come in. Like I said, yeah, please do take care. Have a great day. It's a Friday. I'm sure you guys are saying TGIF. Thank God it's Friday, hey? And all sorts of other things. But thank you so much. It was really good. This is Mr. Mac signing out. Yeah. See you on the flip side. Okay. Ruona. If I don't know, it will Ruona, it will depend if you understand the I don't know if you're in grade 12. If you're in grade 12, okay, I just derived I was applying the power rule. Okay, the power rule. Okay. So if I'm asked, if you are given f of x, and this is basically the concept of the rule, x to the power n, when you are deriving x to the power n, you take the exponent, you multiply it with the current coefficient, and then you subtract 1. You will always subtract 1 from the exponent. This is the power rule. So x to the power n, n comes down, descends, multiplies with x, or the coefficient that would have been there, which is 1. Okay, it's unfortunate that this one we don't always acknowledge. It's kind of like how we don't acknowledge God in many things, because he is the invisible one, the one who is unseen but is always there and present. So n times 1, okay, is what's happening, because the coefficient that was there is 1, unseen and positive, always. Unseen and positive. All right, but we don't usually write the positive sign, we don't write the 1, because the positive one we don't always seem to acknowledge, but he's there, ever abiding and ever there to stay. So n times 1, x, then we subtract 1 all the time. We always subtract 1 when we are applying the power rule, which is how we are able to derive a particular variable or term. Okay, hopefully you are good. Okay guys, thank you so much again. 9,000 likes, really appreciate it. Thank you. We'll see you again. Cheers.